the next purchase.
Man parkerar så långt så man slipper göra.
Agenda, so. To what? Yeah, we can switch. All right, people, welcome to ICCRG. I'm going to show you the note well until I have a volunteer to take minutes. If it takes forever, you'll just have to read every word here. I need a volunteer. I didn't get one previously. I really need one. Come on.
Either you volunteer or we volunteer you.
Yeah, or you have to read it for half an hour. I mean that. I'm going to read every word to you. I saw Magnus laughing. Please. I'm sure you got it. Thank you so much. And you're doing Jabber, right? Come on. JabberScribe is easy. Somebody. Jabber. Yo, Jabber. Thank you. We got a scribe and a JabberScribe. Thank you very much, people. I'll leave you from the IETF IPR policy document. There's a scribe and Jabber question. A very, very quick update, because I called these things ICCRG draft as this is me speaking as author and chair, just to give you an update here, because I'm an author of both of these. We asked for feedback on Lisa, and as an author, I want to thank the reviewers. As a chair, I also want to thank the reviewers. It was really useful. We're not giving up on it, but we're going to merge it with the thing at the bottom, which is a coupling document, where we're going to change the algorithm quite a bit to make it, I think, a lot more interesting. It's a major update we'll be planning, but this is in the long-term future. So you're going to hear back from us. But this is not the reviews were not in vain. Thank you very much. It's going to be a part of this because it's the same problem space anyway. Okay, today's agenda is pretty packed. I'd like to remind people to keep within their time frames, and I'd like to ask Nicholas to begin. No point in me reading the agenda to you. So.
What's that?
Okay, I can pass them. Just put it here.
This is probably a good place.
Maybe a chair. But it should be standing. It should be standing.
Is it that's not going to work. Why don't you leave this here? I'll move this along. I'll move it along this time.
This is one logistically challenged ICCRG meeting today. It is. All right. Blue sheets.
So, I don't read French. F5.
I guess I'm sorry.
And then if you just push here, next slide.
Yeah, we'll manage.
I don't know if this will be working. No, because it's on. This computer doesn't let you.
Come on, let's not waste time. We can press the button for you. Just say next, that's okay. Yeah.
So, hello everyone. My name is Nicolas Kuhn. I'm from the CNES. Who, for those who know what it is, doesn't know what it is, that's a French National Space Agency. And I'm here to present some results on MPTCP and BBR. Next, please. I just want to quickly go through some myths that you may have on SATCOM systems. I'm short of time, so I will do fast. But basically, when we look at the high-level architecture of networks, even though you may think that satellite networks are quite specific and strange, it's not the case. It's very similar to what you may have in cellular or terrestrial access. It's just that we don't have an actual interoperable standard. That is quite a big problem we have, but that's the thing. Another myth on the next slide is the latency. So basically, indeed, we have some 500 milliseconds latency on the links, but we all know, thanks to all the buffer bloat issues we've seen in the past, and also what has been done through the RIDE project, that latency is not just the signal propagation delay. And also there are many cases, such as boats, plane, and others, rural areas, for example, where you don't have any choice anyway. So you will have to deal with this latency, and honestly, it's not that bad. So next slide, please. This is some browsing experience we have using a real satellite access. On the left, you have a light page. On the right, it's a more heavy page. And even though the large page takes some time to have the data to actually come, once we have the first bits of the connection, everything is quite loaded and fluid. So and also on the light page on the left, you can see that even though it is some search and something that requires some interactivity, it's not that bad. Next, please. The last but not least myth is that we use middle boxes, and that is not a myth. We have nasty middle boxes. We split TCP connections, so we use some transparent compression. That is not that bad, but for the TCP connections, we make our own TCP connections, so we break the end-to-end connectivity. And the main problem we have is that it's difficult to have to support and to consider the whole recent improvements we may have as the servers or as a client. For example, all the TFO things and other things. Next slide, please. We use middle boxes for many reasons, and basically we have a quite specific network. I will not go into the details because we don't have much time, but the main problem also we have is that it's a small community, so it's difficult for us to push some specific modifications to TCP for our use case, because for terrestrial and fixed networks, it's a corner case. But And also we have a scarce resource to deal with. So that's why it's difficult for us to actually push things in servers and client. Next, please. And also, if we look for HTTP1 service, we have 3 different pages here that are loaded. We use OpenSound, which is an open source satellite emulation platform, and we have different cases. We have an IW10, IW60, and we have a very basic TCP proxy at the in the satellite network. And what we can see is that what the PEP, so the performance enhancement proxy that we deploy, can do even better than the IW60, even for the long page. So that's why when it's difficult for us to get rid of these strange boxes, because it provides such good results at the moment for the traffic that is going through broadband satellite networks. Next, please. The thing why we present results on BBR and MPTCP is that we are following what's happening on the transport, and we are constantly figuring out whether we actually need these boxes or not. And there were some modifications in the RFC 2760, such as higher congestion window, packet pacing, and these are the things we see in the transport happening at the moment. So that's why I will present some results of BBR over SATCOM and also MPTCP, because that's a good opportunity for us to have an hybrid access with terrestrial and satellite access. Next, please. So this is a platform we have used for BBR. We have different file FTP applications at the client, downloading files which are hosted by or Cubic or BBR server. Next, please. On the left, we can see the results of Cubic, and on the right of BBR, and the top curve is the good put, and the bottom curve is the state of the queue. We can see that Cubic is acting as expected. Basically, it fulfills all the queue, which on the bottom of the blue, we can see that lots of queue losses happen, and we have an overshoot of capacity. On the right, with TCP BBR, despite the strange satellite configurations we have, the latency and the asymmetric links, we can see that we have a protocol that at the whole can use available capacity and with a low queue occupancy. Next, please. However, when we look at fairness, then we may not agree on what flow rate fairness is and if it is actually useful or not. But what we can see here is that at 200 seconds, all the cubic flows are struggling between each other to actually grab the capacity, whereas with BBR, we have the flows that were first on the pipe that keep the capacity for a long time. It's longer for, we have some latecomer fairness issue with BBR, with our version of BBR at least. So for the moment, we still are running further tests on whether we still needs to have some specific accelerations with BBR. We're looking at more application level metrics, but we think that in looking at the queue occupancy and overshoots, it's quite interesting. However, all traffic flows in the internet today are not BBR still. So the thing is, we still, for the moment, will have to make some TCP splits and so on anyway. Next, please. The other use case I will show you is about the MPTCP use case. This is on the top, the trend for the 5G cellular networks architecture, and at the bottom, the same thing that we can have on satellite access at the moment. We have an MPTCP concentrator here that basically is here because we may not have MPTCP deployed everywhere on servers. So that is a use case we consider, but we are more focusing on metrics that's the relevance of this use case anyway at the moment. Next slide, please. So here we have two MPTCP proxies, one at the aggregator I just showed on the slide before, and the other one at the satellite terminal level, for example. And what we can see here is that we still, I need to precise here that we still split the connection, TCP connection here. And what we can see is that despite the huge asymmetry we have between the links, the MPTCP somehow is of interest for both accesses. Again, that is an unfair comparison because we compare MPTCP that has twice the capacity as every single one, but the huge asymmetry could have results in a lower capacity. But so next slide, please. And that's another important result we have had in these studies. But basically, when we have an MPTCP aggregator, let's say at the terminal side of from one who has a satellite internet access, as soon as we deploy an MPTCP thing at the client, we cannot accelerate the traffic anymore on the satellite link. So today, if you are using satellite access, you will not be able to use MPTCP on this use case. So there have been some discussions on that in the MPTCP mailing list. But another thing is that despite the fact that we cannot accelerate the traffic, still MPTCP is doing better than each of the single accesses. And have another slide, please. Basically, we have made some tests on BBR. We have seen an interesting trade-off between the queue occupancy and the actual throughput that you can gain. How we see some latecomer fairness, but what is flow rate fairness anyway? And but the thing is, we still don't know at the moment whether we will deploy some. We will still need in the future some TCP acceleration on the satellite links when we have only TCP BBR light traffic. But at the moment, the share of we still have lots of cubic flows and lots of other flows that are not BBR. So we will not stop deploying PEPs today. And so we also have worked on MPTCP. I don't know how much time I have left, but we also have worked on MPTCP that seems to manage the large asymmetry we have when we use a satellite link. However, we may do better than that. So that is something we are working on adapting the MPTCP scheduling for specific use cases. Also, one problem we have is that when we use MPTCP at the terminal side, we cannot accelerate the traffic anymore on the satellite link. So that is a problem that we have, and which we are working on. And also one point I wanted to make, that we believe that for the moment, even though we have some good improvements on TCP and lots of work done on TCP, improving TCP for either cellular and terrestrial networks, the satellite cases are so strange that there cannot be one TCP that flavors that work for any kind of traffic. So there always we would always need some specific or small modifications. And next slide, please. So these are the people who worked to preparing the results that have been used for this presentation. And also, if you have questions on the platform we've used, don't hesitate. Most of them are open source or open for researchers anyway. And also, we have an open platform. If you want to do tests on real satellite link, we can help you setting it up and making some research projects. So that's all for me. So if you have any questions, I would be free.
Yes, questions. Quick ones, maybe. Can you handle the question? I can just start.
Hello, my name is Yoshi Nishida from G. This is very interesting experiment for MPTCP. So the link you showed over there, if I access our link over there, can I replicate the whole experiment you did? Or do we need to get more information from you?
Can you repeat the question, please?
Oh, okay. So I would like to replicate your experiment. Mm-hmm. And then the links over there is all the information I need to get to replicate your experiment.
Yes, I have provided on the slides all you need to replicate the experiments.
Okay.
If that was the question?
Yeah, I'd like to replicate everything. That's
Welche
Thank you.
Also jetzt sieht man es schon. Wenn ich jetzt Präsentation starten, dann kommt es gleich raus.
Okay. Thank you.
Die Animationen kann ich jetzt testen. Die Animationen sollten schon gehen. Sehen. Als letztes Mal PowerPoint abgestürzt. Das ist halt wirklich irgendwie so zu gehen. Jetzt geht's ja wieder raus. Schauen wir mal. Präsentieren? Ja, das geht mal. Jetzt werden wir das Display noch switchen. Was ist der Typ? Alright. Should we be switching this to that ourselves? So. Yeah, maybe if that works, that would be great. Yay. Good. Okay. The logistics are interesting at this meeting.
All right, so sorry. My name is Ron Bless, and I'm presenting a paper that was published at the last month at the ICMP. It's about the experimental evaluation of BBR congestion control, and this is joint work with Mario and Martina. So you all know Google's congestion control BBR because they already presented it, I think, 3 times here. So the overall objective was to replace loss-based congestion control because our belief is that we can do better in the community, I think. And the goal was also to achieve high throughput, but with a small queue. And it's basically a model-based approach. And you see the model here. On the right-hand side. So we did some experimental evaluation based on the original publication in the ACMQ paper and the Linux 4.9 implementation. And so our key findings are basically that the model does not work very well for multiple flows at the bottleneck, that it causes massive packet loss in small buffers, and it also has different kinds of unfairness, especially with respect to suppression of loss-based congestion controls. So what's wrong with the model? So the network model is fine for the bottleneck, but BBR uses this at the sender, and that basically lacks the dynamics of multiple senders. So that's one of the problems. So the behavior in the single flow case is quite straightforward. If you have only a single flow, for example, at 100 megabit bottleneck, you see that as soon as BBR probes for more bandwidth, it will see, so the delivery rate here, it detects is a dashed line. One round trip time later is basically the same because there's not much more bandwidth to provide. So in that case, it tries to reduce the queue that has been built by the down phase in the gain cycling. So the flow probes and cannot get higher delivery rates since the bottleneck is already fully utilized. So, and the excess data is then removed afterwards. So far, so fine. So that's also what we saw in the experiment. So in our test setup, we used 1 gigabit per second bottleneck. And you can see here the throughput. The little dips here are basically the probe RTT phases. And if you look at the RTT, you can also see nicely the probe bandwidth cycles here and the probe RTT phase. So everything works as expected since the model fits. But what about the multiple flow case? So if we have multiple flows, let's assume we have the simplified case, 2 flows now sharing the 100 megabit per second, so that we have 50 megabit each, and we're starting with one flow that starts to probe. And so the gain cycling phase up will then try to get more bandwidth, and it actually gets more bandwidth because the other flow then basically loses bandwidth. So the first flow that is probing actually measures a higher delivery rate, and that leads to the in the next phase to using that higher bandwidth it just saw due to the maximum filter that is also applied. So the windowed maximum filter keeps the send rate now at the new high level, and the other flow also keeps its sending rate at the old level due to the maximum filter. So that basically means that for multiple flows, both flows together, so this chart here shows basically the individual send rates and the combined send rate, which is the red line here. And as you can see, both flows together actually are way above the bottleneck capacity. So since this is a rate-based approach, the amount of in-flight data actually steadily increases, and the bottleneck becomes overloaded. So in our paper, we have actually a proof that this is a consistent behavior of BBR. So what does that mean? In a large buffer, which means the buffer is at least a BDP large, BBR basically operates at its in-flight cap, which means you have 1 to 1.5 BDP queued. So BBR's operating point is not at the optimal point that the paper pointed out, but it's more or less depending on the buffer size. So it's here, for example, at 2 BDP maybe. So in a smaller buffer, actually, what happens is that now, since the right side here is shifted to the left, you will find the operating point of BBR even beyond the point B here. So Cubic's operating point is here, while BBR's operating point is even above the buffer size capacity. So our experimental evaluation setup looks like this. So we used basically several PCs and a hardware switch. So the sender here has 3 10 gigabit per second interfaces, the receiver on the other side also, and we have a software-based DPDK switch, which allows us to look into, let's say, queue states, and also perform delay emulation if required. And we have the bottleneck here, 10 gigabit per second link, which is then attached to another switch. So we have a typical dumbbell topology for the 10 gigabit per second experiment. And we have a little bit simplified topology due to restrictions of the transceiver speeds. We needed a dedicated 1 gigabit per second link because these interfaces were not able to switch down the link speed actually. So we used the 4.9 version implementation of BBR and used bottlenecks at 1 gigabit and 10 gigabit per second. So the RTT was around 20 milliseconds in most scenarios, and we had 2 types of bottleneck buffers. The large version is 160 milliseconds, while the small one is 60 milliseconds. So these correspond with the base RTT to 8 BDP or 0.8 times the BDP. The sender is not application limited. We use IPERF3 for that, and we repeated every experiment at least 5 times, and I'm showing always the results of single representative runs. So let's start with 2 flows and a large buffer scenario. So 2 flows with the same minimum RTT. The prediction of the model says that basically the BBR is operating at its in-flight cap, so BBR uses or queues 1 BDP in the buffer, and that can be seen here. So we have an RTT, base RTT of 20 milliseconds, and this is basically doubled nearly all the time. The two flows are active, so a single flow operates at the base RTT, but as soon as the second flow starts, we have 1 BDP queued. So if we increase the minimum RTT to 40 milliseconds, this should double, and this is what we also can see here. So it's now then the effective RTT is at 80 milliseconds. And so if we use 80 milliseconds RTT min, we see that the effective RTT doubles at 160 milliseconds. So multiple flows in a small buffer, where small is not really small, it's 80% of BDP. So if we use 6 flows, which means 2 per interface here, BBR causes massive packet loss because the operating point is, as just explained, even beyond the buffer capacity. So if you look closely at the sender's transmission rate here, you can see that you're sending above bottleneck capacity actually. So it's even beyond 1 gigabit per second. So we have roughly here 10% overload. Sorry, what about cubic? Cubic in the same scenario doesn't cause such a massive overload of the bottleneck. It smoothly more or less operates at the 1 gigabit per second capacity. And if you compare it, the number of retransmissions, for example, you can see basically that in the small buffer scenarios, you have 3 orders of magnitude differences actually with respect to the numbers of retransmissions. So that's quite a lot. What about inter-protocol fairness? So if you let BBR run versus cubic, for example, in this case, we have 1 gigabit per second bottleneck, 1 BBR flow against 1 cubic flow, and we have small buffers. So BBR basically suppresses the loss-based congestion control here because, yeah, BBR is so aggressive that it causes basically packet loss, and cubic then backs off while BBR tries to get as much bandwidth as possible. But this still more or less within the model of BBR because we only have a single BBR flow. So our expectation was that it gets worse as soon as you start an additional BBR flow. And that is really the case. So 2 BBR versus 2 cubic flows, for example, now the model doesn't hold anymore. And in that case, multiple BBR flows simply behave more aggressively. You can see the start of the second BBR flow here. Around this point in time, basically the bandwidth of the cubic flow drops down even more, and even a second cubic flow isn't able to get any reasonable bandwidth here. So loss-based congestion control in small buffers gets severely suppressed if you have multiple BBR flows, because, as explained earlier, the operating point of BBR is here, and at least in the version that we tested, it doesn't react to packet loss. So congestion, packet loss as congestion signal is basically ignored. So intra-protocol fairness is also interesting. So again, 6 flows here, 20 milliseconds RTT. We were not able to find any real consistent fairness behavior. So you can see different scenarios like more or less fair share of the bandwidth, or sustained phases of few flows getting only a small portion of the bandwidth, while others get most of it, and something in between. And also here, even in a small buffer, sometimes you see quite good fairness. So what about RTT fairness? Since the prediction is that BBR operates at its in-flight cap, and the in-flight cap then basically is calculated on base of the seen RTT and times the available bandwidth, so the bandwidth delay product. we just use 20 milliseconds, 40 milliseconds, and 80 milliseconds as base RTT for 3 different flows flowing at the same time. And so the prediction is that each BBR flow operates at its in-flight cap of 2 BDP in a large buffer. So we have a large buffer scenario here. And as you can see that the flow with the largest RTT basically, which is the red one here, gets the most of the bandwidth share here. So the 20 millisecond flow is nearly here down at the bottom, while the 40 millisecond flow still gets some share. So this is due to the fact that the larger RTT means more data in flight, and this directly leads to unfairness. So flows with the larger RTT have basically an advantage here. So to summarize that, BBR is basically a model-based congestion control and works well if no congestion is present. So for a single flow at the bottleneck, it works perfectly, right? But for multiple flows, BBR steadily increases the amount of in-flight data. And so in large buffers, BBR operates at its in-flight cap. It also has a consequence of showing RDT unfairness. And in small buffers, we saw a high amount of packet losses because BBR also ignores packet loss as congestion signal. So we found no consistent fairness behavior, and especially we saw unfairness to flows with loss-based congestion control, Cubic or Reno, for example. So as you all know, BBR is already in use, but probably right now it's mainly application limited where it's used. So we maybe don't see these kinds of effects, and these were all more or less generated in a lab. So that's kind of maybe not a real world scenario, but still think worth to think about. So BBR is still under development, and I think Neil will give an update on further further development of BBR, right? Questions, yes.
Questions.
Oh, wow. All right, well, this is good. We have a big room and no questions, but we're gonna get another one about BBR. So I suppose probably the questions are gonna come at the end of the BBR slot. Oh, okay, there is one.
Stuart Cheshire from Apple. Thanks for this work. I think it's very interesting. One thing I was wondering about is BBR has a cap of 2 times the bandwidth delay product, but to work that out, it has to know what the bandwidth and the delay are. Once it's got too much data in flight, I was wondering if there's then a risk that its estimate of the round-trip delay will be inflated because of the overfull buffers, which means its bandwidth delay product estimate and the cap of that grow, and the thing spirals out of control because it's actually not getting the accurate data. And it sounds like you didn't see that. I wondered if you had any intuition of why.
No, actually, we see that. But basically, for example, in the beginning of, so if the flow starts, you basically see, or the flows will measure actually a higher effective RDT. And in this case, you have more or less some kind of latecomer advantage, right? And that's what we saw. But after some time, actually, BBR is able to more or less synchronize the flows going into probe RTT, and then they have more or less the ground truth of seeing the right minimum RTT, and then that corrects itself. But as you're right, so in the beginning where you have a strong overshoot, so we saw flows actually having more overshoot when they're in the starting phase. Right.
Thank you.
Well, this is Jeff Houston from APNIC. We've done experiments like this over the internet, where we were using data centers in Frankfurt, London, and Australia. And the one between London and Frankfurt was actually interesting. It's a short RTT, but it's across the production internet. And BBR running on standard Linux with 3 parallel flows, same endpoints, was doing a sustained 50% packet loss rate, but maintaining 300 megabits per second stably. So it's this sort of, it brings up basically 2 BDP. Like that's, the theory and practice are exactly the same, but this sort of bizarre behavior that absolutely sustained massive loss rate. When I tried to bring in Cubic or Reno, no packets went. You know, they just got crowded out on loss, as you'd expect. So it stabilizes at a phenomenal loss rate. When I do Germany to Australia, it hits about 140 megabits per second, which is great on the production internet. Interestingly, though, the loss rate is way down. It's only on short delay. It finds this sort of stable point just beyond a full queue and sits there happily.
Right.
Which, you know, if I want everyone else to die, I'm a happy little person.
So, Jana, I'm going to address, number of threads here. But just very quickly, there's the RTT inflation doesn't really happen because BBR uses for its BDP estimate, it uses the minimum RTT measured. So it's not the continuous RTT or the SRTT or the instantaneous RTT. So the minimum RTT is measured. And as Roland pointed out, there is a probe RTT phase which happens, which is designed to allow flows to measure a minimum RTT so that during periods when the network is not fully utilized. So that's one thing. I'm definitely curious to see more. If you have data on this, that you clearly do, I'd love to see this. Have you published this? It would be wonderful to have this data. I'll just say that Neil has a presentation coming up which might address some of these points.
Yeah, I think we should try and get to that. So thank you very much. Let's see if we manage our first remote presentation. I don't know how to do this.
Can you guys hear me?
Yeah, we hear you.
Oh, yeah? Okay. Can you see me?
We see you. Should
Wow.
I be showing your slides or is it somehow
Yeah.
magically happening? I think I should probably.
Yeah, I think you have to do it on your end.
Yeah. Let me see if I can. Where's this adapter?
Neil, are you in a spaceship?
I wish. No, I'm actually in New York, and it's past 1 a.m. here. So if I doze off, will somebody yell at me?
Like that, maybe. Nothing happens. Okay, I gotta go to presentation mode. Slideshow, does it do anything? I hope. No, it doesn't. All right, I'll. How do I do this? Is it a way of? I keep waiting on the back. Copy that. Just a second. Almost there. Mirror, yeah, show mirroring options. Yeah, totally show them. Arrangement, color, come on. Color windows, arrangement, mirror displays, that should be it. Yeah, easy. Okay, how do I remove it? Yeah. That was it. Okay, good enough, I hope.
Looks good.
All right. Go ahead. Sorry for the delay.
No problem. Thank you. Yeah, so my name is Neil Cardwell, and I'm going to give a quick update. I guess I just have 10 minutes on recent work we've been doing at Google on some updates to the BBR algorithm. This is joint work with the folks you see there. Yeah, so we're going to start out with a quick review, super quick review of BBR version 1. We'll make it quick since Roland did a nice job of summarizing version 1. Then we're going to dive into some recent work that we've been doing on BBR version 2. And then we're going to focus our discussion on the behavior in shallow buffers, since obviously this has come up in Roland's talk and in the Q&A session afterwards. And then we'll have a quick conclusion. Next slide, please. So the motivating problem here for BBR, as has been mentioned, is that there are these issues with loss-based congestion control. If the packet loss comes before the congestion, which can happen in shallow buffers or with bursty traffic or random loss, then your loss-based congestion control can get low throughput. But on the other hand, if losses come after congestion, which happens in deep buffers, you get the problems that people have called buffer bloat with high delays. Next slide, please. Next.
Do you want to take let him take questions? Is it okay to take questions now?
It's such a short talk. Maybe we can hold them till the end. Does that work?
Okay.
Yeah, I'm worried we'll get bogged down.
No, this is quite important, Neil.
Oh, okay, sure.
If it's important, then we have to.
Okay.
Of course, then.
Bob Briscoe.
Make it short, please.
Sure.
Packet loss alone is not a good proxy to detect congestion.
Bob, wait.
Where was the evidence for that?
No, actually, wait. Seriously,
Right.
just wait for this.
So BBR is basically a new kind of approach that builds an explicit model of the network path. And version 1 had just the maximum bandwidth that's been recently seen and the minimum round trip time. And it uses that model to control its sending and to try to vary its pacing rate and CWIND to try to explore the network and build feed samples to that model. Next page, please. So, just a quick summary of where we've been so far. So with BBR version 1, we've deployed it at Google for TCP and quick traffic on google.com and YouTube and WAN backbone connections. The code is available in Linux TCP and quick. And there's also active work on BBR going on at Netflix, and we're in close communication with that team. There's some internet drafts describing the algorithm, and we've presented it at IETF, and there's a sort of an overview paper in the communications of the ACM. Next slide, please. So currently we're working on improving the BBR algorithm, and the effort is sort of continuing on multiple fronts. One of our big emphases is reducing the packet loss rate in shallow buffers, which has been discussed nicely today. This means that we're trying to tune the algorithm so that it can handle both deterministic and stochastic loss in a reasonable way. And alongside this steady state improvement, we're also working on a faster exit of the startup mode in the presence of packet loss. We're also working on reducing queuing delay in general, but especially that helps in deeper buffers with an approach that essentially paces at a lower rate with a gain below 1, a pacing gain below 1, to try to pull the in-flight down closer to the estimated BDP on a more frequent basis, say once per gain cycle of 8 round trips. And Randall Stewart came up with a nice name for that, a nice buzzword, drain to target. We're also working partly through the previously mentioned mechanisms of reducing losses and reducing queuing delay, but also through some other mechanisms. We're working on improving fairness, both between BBR flows and with loss-based congestion control. That's sort of a lengthy topic, so we'll have to get to the details on that another day, another IETF. Another area where we're working is on improving the BBR throughput in Wi-Fi and cellular and cable networks, where we see all sorts of very common ACK aggregation and decimation features. And the work there is sort of in 2 areas. One is improving the bandwidth estimator for this case, and then the other is making sure we provision enough data in flight by modeling ACK aggregation. And we're seeing pretty decent results with the latest Wi-Fi LAN testbed increasing bandwidth from 40 megabits with version 1 to 270 with version 2. And we're working on improving behavior in the data center with lots of flows. And basically the goal is to use BBR for all Google TCP and quick traffic, whether it's data center, WAN, or public internet. Next slide, please. So we've deployed a couple smaller scale changes in the Google's network so far, and those are running in production to see how those behave. So far, they seem to be doing fine. Next slide. So just a quick comment on the sort of the major issue we've been focusing and that has come up today a lot. So BBR has a known issue with behavior in shallow buffers, which Roland discussed in some depth. And the root cause has to do with interactions between the bandwidth probing and the bandwidth estimator. And a core part of this is basically that the bandwidth probing is based on a simple static proportion of the model parameters. So we go at 1.25 times the estimated bandwidth once every 8 round trips. And this was based on a set of competing trade-offs among real-world issues that we saw in real deployments. Cell systems often have dynamic bandwidth allocation, so they need a big backlog, whereas shallow buffered switches with lots of bursty traffic, they need some compensation for that stochastic loss. So there are a couple of different trade-offs going on here. But basically for BBR version 1, we aim for simplicity and robustness in the cases that we were deploying it in. So we had a sort of one-size-fits-all static probing system. The BBR version 2 is going to use a dynamically adaptive approach that I'll discuss briefly here. So next slide, please. So there are a couple different changes here. One, I would say there are basically 3 main buckets into which these changes fall. The first one is a generalization and a simplification of the long-term bandwidth estimator, which was previously only targeted at scenarios with policers, but we sort of generalized it to apply to fast recovery in general. And here the bandwidth estimate is a windowed bandwidth average over the last 2 to 3 round trip times. The second big change is some new algorithm parameters to adapt to shallow buffers. Not surprisingly, we have an estimate of the maximum amount of data that we think we can safely inject in flight into the network before we think we're causing loss. And second, we have the current volume of data that we're going to use the next time we probe the network to see if there's more capacity. And it starts gently at 1 packet and then doubles upon success to rapidly explore if more bandwidth suddenly becomes available. And then the third big piece is a sort of new full pipe and buffer estimator that uses a loss rate signal. Current iteration is just using something simple, looking at the loss rate over the scale of a round trip being 5%, but we're looking at other alternatives as well. And once that estimator estimates that the pipe and buffer are currently full, it takes some steps that won't be surprising to people in this room. We set the estimate of the maximum safe volume of data that we can have in flight to the current flight size. Then we do a multiplicative decrease of the in-flight cap to 0.85 times that estimate. And then we wait at that sort of backed off level for an amount of time that is currently a sort of scalable function in the 1 to 4 second range as a function of the estimated bandwidth to give us a sort of RTT fair mechanism that also can reprobe bandwidth in a sort of reasonable amount of time. And this also gives us a sort of design curve that we can adjust to trade off how gentle we want to be on Reno and Cubic versus how reasonable we think it is to wait, say, the way Cubic waits 40 seconds for reprobing bandwidth if you're running at 10 gigabits, say, or even 18 seconds if you're running at a gigabit and your RTT is 100 milliseconds. Anyway, so that's a discussion for another day. But this is continuing work. Next slide, please. So this just is a scenario to give you a sense of how this behaves within the V2 approach. So this is 100 megabit path, 100 millisecond RTT, very shallow buffer. It's just 5% of the BDP. And this is just a 60-second bulk neck perf transfer with 6 flows, staggered entry times. So this is sort of comparing Cubic, BBR version 1, and then the current iteration of BBR version 2. With throughput on the left, you can see that basically Cubic has some nice fairness properties. BBR version 1 does not have the level of fairness that we'd like, but BBR version 2 has pretty decent fairness and sort of approaches Cubic. And then the retransmit rate, Cubic's is nice and low, less than 1%. BBR version 1, as has been discussed, is pretty high. Here it was 15%. And then BBR version 2, the current iteration, has a loss rate that's about an order of magnitude lower than BBR version 1. That's in the neighborhood of 1.3, 1.4%. Next slide, please. And this is just a picture to sort of give you a sense of the convergence properties and the fairness properties of the various flavors here. So we've got cubic on the top, BBR version 1 in the middle, and then the current iteration of BBR version 2 on the bottom. You can see basically BBR version 1's fairness issues there, and then you can see that cubic and BBR version 2 do a nice job of leaving a little bit of headroom there in terms of idle space so that new flows can come in and discover the available bandwidth. And you can see that, it's cubic and BBR version 2 are not constantly riding right up against the 100 megabit mark so that they can keep the loss rate nice and low. All right, now next slide, please. So that was just a quick discussion of BBR version 1, and then sort of a quick taste of BBR version 2. And work continues on both the Linux TCP implementation and the Quick implementation at Google. And as I said, there's some nice work underway for BBR in FreeBSD TCP at Netflix. And of course, we're always happy to hear more test results and more research results as we continue to work on BBR on our end as well. So I guess next slide, and then any questions.
Yeah, questions. Bob. Okay.
Do you want to say it again?
Hi again. This is Bob again. Yeah, the question on where did the evidence come from that loss is not a good estimator for congestion. I don't think we've seen any evidence for that, and I think that's sort of one of the underlying problems here, in that there's this sort of prejudice against using it, whereas it's all information that you need to have. I know you've started to use it here, but you haven't really used it. You've just sort of tried to avoid it.
So I wouldn't say that we're trying to avoid it. I mean, I think we are trying to use the loss signal here. But anyway, back to the question about what we think about loss and its relationship to congestion. So the way I think about it is that, as I said early on in the slides, it's very common, for example, for buffers to be very deep, the well and often discussed buffer bloat problem. So that's one end of the spectrum at which, because you have this deep buffer, it gets once it's congested essentially once the pipe is full and you have a little bit of queue. But the packet loss doesn't happen until the queue gets way out of control and quite a bit too long. And so, that's one case in which packet loss is not a good proxy for congestion, because congestion happened very early and then the packet loss happened when the queue got to be seconds bigger. So that's one end of the spectrum that we definitely obviously see. It's well described in many contexts. The other situation where we see that there's this real disconnect between packet loss and the point of congestion is in high-speed, shallow buffered WANs. So if you have a network that you build out of commodity switches, and let's say they're operating at 10 gigabits or faster, and let's say that your switches have some number of megabytes of buffer memory, because they're just commodity switches, they're what you could afford for your very large high-speed network. So in this case, if you have a couple of megabytes of switch buffer and you're going at 10 gigabits or faster, then often in these scenarios, then you have just 1 or 2 milliseconds of buffer space, essentially. And if your round trip time is, say, 100 milliseconds or 200 milliseconds, which can obviously happen, then you can, and we do see in Google's high-speed WAN backbones, that you get these scenarios where a flow is operating with 100 millisecond round trip time, and during that 100 milliseconds, there can be all sorts of little bursty congestion episodes where that 2 milliseconds of buffer fills up, and then it drains, and then it fills up, and then it drains. And you can have any number of little bursty congestion episodes during your RTT. And if you use traditional Reno or cubic style loss-based congestion control, then basically operating in the environment, every round trip time, you would get a signal that you interpret to mean slow down. And no matter what you do, you get a signal to slow down. But meanwhile, there could be that link could be 90% idle because maybe there's 90 milliseconds of total silence and only 10 milliseconds split up into little chunks here and there where that 2 millisecond buffer was full. So this is the other kind of environment that's important, at least to us, and it's an environment where packet loss is not closely related to congestion. Sorry for the long answer, but it seems like a core question.
Maybe the next answer could be a little shorter.
Sorry.
And maybe I'll just say I'll cut the line after Stuart. So I appreciate this discussion, but let's keep it limited.
So in that case where you've got these little episodes of loss during a round trip time, I think what BBR is trying to do by effectively trying to ignore that, it's holding, if they are other flows coming and going, the short flows, if you like, then it's holding the buffer high, and then they are taking it higher rather than trying to respond slightly to them so that there's a bit of buffer for those small flows coming in. In other words, all these the assumption that loss is not really loss or it's not really congestion means that BBR is holding or going at a certain delay level in the buffer or higher, rather than trying to go slightly under to allow all these other little things to happen.
Well, I think that's a fair description of BBR version 1. I think, as you probably saw in the presentation, we're trying to incorporate the kinds of considerations that you are mentioning right now. So I think we are on largely the same page as far as that particular issue is concerned. We want to respond to the bandwidth that's actually available to the flow, and we want to use loss as a signal to do that, in addition to the delivery rate and the round trip time of the path. We want to use
precisely.
Yeah.
Andrew McGregor, I just wanted to add a comment to what Neil said there, and actually I end up with two. One is that it's not like inside Google we don't care about packet loss, because it costs us a substantial amount of RAM, and the cost of that is quite significant. And the second thing is that those aren't the only environments where you get non-congested loss. I mean, the other classic case is Wi-Fi, and there are things that happen in lots of networks in, shall we say, poorer and more remote parts of the world where the overall loss rate is some kind of indication of congestion, but it's not a reliable indication of congestion in the way that it was designed to be in Reno. So I think BBR2 is going, and by the way, this is the first time I've heard exactly what Neil's planning with BBR2. I think BBR2 is heading in the right direction of softening all the responses to some kind of reasonable control algorithm, rather than being super, super hard on everything. And that was BBR1's mistake, being super hard on those variables.
Yeah. That wasn't a question, it was just a comment, so we can get to the next question, right?
Sounds good.
Okay.
Mia Kulevind. So I saw that you have this kind of threshold, and they're like 5% of loss, you do something. So that's already great. So you don't ignore loss completely. I think this is really important for the safety of the internet. However, 5% seems still high. So I guess that doesn't solve the fairness problem you have with loss-based congestion control, right?
Well, it doesn't in itself solve the problem. That's true. But I think there are a number of things to think about in there. So the loss rate there in that threshold is well, first of all, this is just the current iteration of BBR, and we're also evaluating other alternatives. But second, the loss rate there is actually just sampled over one round trip time, and so it's a different matter than what you might be thinking of when you think about 5%. It's not 5% globally across the lifespan of the flow. It's just in that round trip time. And at the BDPs that most Reno and cubic flows run at, you hit 5% pretty quickly due to the quantization. But anyway, so let's see, the other consideration I think to think about is that what matters to Reno and cubic in terms of what they can utilize and in terms of bandwidth is not really the loss rate as it would be measured with loss counters, but really the distance and time between the loss epochs. And I think right now, I'm thinking about it in terms of making sure the loss epochs that BBR might create are far enough apart that Reno and cubic can get decent bandwidth as they ramp up in between those loss epochs.
That's future work, I guess.
Well, no, that's in the algorithm, but I guess tuning the exact relationship between current bandwidth and that interval is something we're actively working on. And I think you heard some of my thoughts about, we want to be reasonably fair to these algorithms, but A, they're not really fair to themselves. B, they're not really RTT fair to themselves for sure. And then C, they have some unreasonably long timescales for adjusting in some cases. So I think it's going to be tricky to pick that curve, but I think now we at least have a dial in the algorithm to choose this explicitly and consciously.
And then I have a quick comment. So for data centers, if you want to distinguish loss from congestion, there's a much easier solution, which is called ECN.
Yeah, fair enough. Absolutely.
Okay. Last one.
Stuart Cheshire, Apple. I know we're short on time, so I'll make this brief. My comment is kind of along the same lines as Bob's and sort of along the same lines as Jeff's about massive packet loss. What concerns me is we have this belief that I hear repeated that loss is not always due to congestion. Sometimes it's just random stuff that happens. And I hear this a lot from my management at Apple, people who studied computer science but not networking. And the one thing they remember from their networking class is that the internet loses packets all the time. And therefore, TCP is wrong to treat that as a sign of congestion, because it's not. It's just the way the internet works. It's throwing packets away for no reason all the time. And that may or may not be true. It may be that there are Wi-Fi algorithms that are over-aggressive with the transmit rate they pick, and their rate adaptation is not finding a reliable operating point. But if that's true, the question is, what do we do about it? And one answer is we put bigger buffers in these switches. We improve the Wi-Fi algorithms so that random loss is not happening at quite the same level. That's one approach. The other approach is to say, oh, forget it. Let's just ignore loss. Loss means nothing anymore. If you lose packets, go faster. Power through the loss. And what I'm concerned about is sure, that works in small-scale tests. But if Apple and Android were to upgrade, and Microsoft were to upgrade, basically 90% of the hosts on the internet to be using this strategy, if you've got 50% packet loss on every link, then after 10 links, you've only got 1 in 1,000 packets getting out the other side. And I worry we'll be in a situation where we're all dumping a fire hose of data into the network and basically nothing is coming out the other side. And that takes bandwidth on shared links, it's using Wi-Fi spectrum, it's using battery power, it's consuming a bunch of resources for data that doesn't survive to the other side.
Right. So I think you heard basically during the talk that the issues that you were just mentioning are the things that definitely happen with BBR version 1. And we are absolutely taking these issues head on. And as you heard in BBR version 2, there's going to be the loss signal explicitly factored into the response of the algorithm in terms of how it estimates whether the pipe is full and how it backs off, and then how long it decides to stay backed off. So I think with BBR version 2, I think you'll see something hopefully more to your liking. We'll see when we get to the next IETF.
All right. Thanks. It was a good discussion. And way over time, but good. It's okay. All right. Bye, okay. Neil, and handing over to
Yeah, this is Roland again. So this is joint work with Mario, Felix, and Martina. It's about TCP LOLA, which is an approach toward low latency and high throughput congestion control. So the motivation is to achieve high throughput and low delay. So this is typically considered as a trade-off or even as conflicting goals. So we think this is not necessarily so, and so we try to mitigate actually this trade-off. So there are several approaches here, you all know, like AQM or tweaks to existing congestion control in combination with AQM, like this alternative backoff with ECN, so that you can keep the utilization high even if you have AQM and traditional loss-based TCP operating on that. And yeah, there's also the other approach of trying out new congestion controls. So we wanted to investigate how far we can actually get with a congestion control, achieving low queuing delay, high utilization and throughput. We want to be scalable, so that means that we can also use even 10 gigabit per second and beyond. So several orders of magnitude of bandwidth that you need to scale with. We want to achieve even RTT fairness. And the whole approach should work with, at least in the beginning, with regular tail-drop queues. Our focus was basically on wide area networks and not data center networks specifically. So this is not excluded, but wasn't in our initial focus. So the general goal is basically, if at least in our point of view, to determine a suitable amount of in-flight data in order to achieve high bottleneck link utilization. So on the other side, we want to avoid creating any standing queues in order to keep the queuing delay low. So what LOLA does is it provides a configurable fixed target delay value. So we can say we want to have a queuing delay below more or less 5 milliseconds, for example. And in our definition of congestion, we think that congestion is when we see a persistent queuing delay above the fixed target. So the challenge then is basically also to achieve good convergence to fairness, so that the problem is you may end up with, if you only want to achieve the first two goals without considering fairness, you may end up with a total amount of in-flight data which is quite okay, but you may see unequal rate shares. So the idea is then that basically you need to increase the in-flight data of one sender while reducing it for others. And this particular challenge is if you have a small queue, the flows more or less interact via the queue. And so you have less room then for interaction if you want to keep the queuing delay small. So this is basically more difficult. And we want to do that without sacrificing the low delay goal. So not allowing overshooting in the queue, for example, in order to probe aggressively for more bandwidth and so on. So the basic approach is that we use queuing delay thresholds. So this is showing the bottleneck buffer queue here. And we define more or less the areas. So one, the first area is below a threshold target called Q low, where the link utilization is basically unknown. So because that is more or less maybe measurement error or noise. So we cannot be sure that below that threshold we have a reasonable link utilization. So once we cross that threshold, we are in an area which is kind of okay because the queuing delay is still under control. So we try to stay below Q target, which is, as I just briefly introduced, maybe set to 5 milliseconds, for example. And so we want to achieve in this green area here high throughput and low delay. But once we got beyond Q target, we have a state of congestion and we try to actually back off then. So we need to estimate the queuing delay. Right now we're using a minimum filter over a fixed time period in order to measure the standing queue. And we also have a heuristic in order to adapt to any network path changes. So for example, if you have path change and the minimum RTT actually increases, then you need to adapt to that once in a while. So overall, LOLA is a congestion window-based approach. And we also use packet pacing, which is beneficial for its operation in order to get better measurements, but it's not necessary as, for example, in BBR. So the flow states, or it works roughly like this. We have a slow start phase, which is nearly as always, doubling the sending rate more or less. So we have some exit condition where we try to exit early in order to avoid overshooting too much in the queue, into the queue. Then in this yellow area here where the link utilization is unknown, we are starting just like cubic to increase the congestion window until we basically cross this queue low threshold here. Once we cross that, so the estimated queuing delay is larger than queue low here, we enter a mode which is called fair flow balancing. So this is a special state where we try to achieve fairness, which is explained on the next slide. And then once we actually cross the queue target delay, so when we enter more or less a congestion state, each flow holds its congestion window for some time in order to let others detect actually that they crossed altogether this state here, or the target here. And then this is also important, some action is triggered, namely in the so-called Taylor decrease. So this state, or this action tries to actually drain the queue completely, but still keep the utilization high. So each flow tries to reduce the congestion window by a suitable amount, actually, of data. And then you're going back to cubic increase and so on. So you have more or less a cycle. So how does that flow balancing work? So it's a novel convergence to fairness mechanism. So it tries to actually equalize the amount of data that each flow may queue at the bottleneck. And the challenge is here to also dynamically scale the allowed amount of data with respect to the given delay target. So it depends basically also on the speed that you're operating, so the throughput and so on. The problem is that the knowledge about the current shares is actually not available. So we need to basically try to come up with some heuristic in order to achieve fair share. So a flow with more currently having a larger congestion window than the fair share just keeps its congestion window. So for example, the green one here starts alone, and then the second one joins here. And as you can see in these gray areas here, which is the phase of fair flow balancing, you can see that the green one always keeps its congestion window until they more or less come together. And the other flow here, the flow with a smaller than the fair share, actually increases its congestion window, as you can see here. And this curve here is cubic in order to be scaled, or in order to be scalable. So we have a simple heuristic to use or calculate an allowed amount of data in the queue, more or less a fair queue share, if you will, which is time dependent. So over time, actually, the allowed amount of data in the queue increases. And now the problem is then that you need to more or less synchronize at some point in time, but that point of synchronization is basically that event here. So there's the good chance that every flow will reset its timer then. So the testbed setup is nearly the same as in the BBR case, so this don't tell you much about that, but the queue low target was, the queue low threshold, was set to 1 millisecond, and the queue target was set to 5 milliseconds here. Synchronization time is set to 250 milliseconds, and the measure window actually is set to 40 milliseconds. These values are not really optimized. So there's much room for improvement maybe. And so let's look at the results. So 2 flows sharing 10 gigabit per second. So the first flow starts and is able, actually the green one here, is able to fully utilize the bandwidth. Second flow starts, and then you can see that they're starting the fair flow balancing phase here. And basically, yeah, they achieve a quite fair share here. In comparison to other delay-based approaches like TCP Vegas is basically not able, even with a single flow, to utilize the available bandwidth because it basically misinterprets jitter as congestion signal, and therefore it backs off too early. And so fair share is also not achieved. So trying to keep the queuing delay low is also the second goal, high throughput, low queuing delay. And as you can see, if you plot here, the RTT basically single flow just sails smoothly, and then the second flow starts. Both flows do their fair flow balancing phase, and you can see that you have always just little spikes here, which correspond to the 5 milliseconds queuing delay target. In comparison to that, as already known, cubic TCP always fills the buffer completely, and this also leads to higher queuing delay in scene RTT. So the queuing delay basically is also RTT independent. We varied, for example, the RTT in this case to 5 milliseconds, 61 milliseconds, and 101 milliseconds. And as you can see, always Lola just adds 5 milliseconds to the base RTT, and so it keeps the target of 5 milliseconds queuing delay actually. So the queuing delay is independent of the base RTT and also the rate, which is not shown here, and also with respect to the number of senders, which can be seen in the next slide. So we have several flows starting here in succession. In this case, there were 18 flows. Just for clarity, I show only 2 flows. But it's nearly the same for the others. So in this case, even while we have several flows starting here, Lola is still able to control the overall queuing delay and basically produce no packet loss. So in contrast to that, comparison to BBR, for example, BBR flow start in succession, you can see that BBR first fills the buffer completely, even overshoots sometimes, and then yeah, that's this is measured basically at the sender, and it also produces several retransmissions here, as you can see. So what about RTT fairness? RTT fairness can be even achieved by Lola in the sense that yeah, if you have 2 different flows with different RTTs, they are able to get a fair share nevertheless. This is showing a small buffer scenario, so you still converge to fair shares, even though they have different RTTs, 21 milliseconds and 101 millisecond base RTT. So in comparison to that, Cubic isn't able to achieve fairness here because it just converges to similar congestion windows, but the flow with a larger RTT needs to have more in-flight data, and so the flow with a larger RTT isn't able basically to completely get a larger share here. So this is just the showing first test of the overall concepts. So this was published on the LCN conference last month. So the parameters are not thoroughly optimized yet. It's not a full-fledged TCP variant, so you just are looking into several aspects, and so there's room for further investigations, like use of one-way delay instead of RTT measurements. Right now we're using the RTT, but it's also easy to use the one-way delay instead in order to get rid of any disturbances on the reverse path. We didn't look into the issues of delayed and compressed X. Furthermore, we don't know how it behaves in wireless environments. Also, multiple bottleneck scenarios may be a problem. And we also did some work on coexistence with loss-based variants, but we don't want to build in any compatibility mode, but instead use separate queues, for example, or maybe also AQMs. So what we plan is not to rely on indirect measurements of queuing delay, but instead use explicit feedback from the network. And so we are doing more research in this direction.
Thank you.
You're welcome.
All right. Thanks for being faster than planned. And any
planned for 50
quick
minutes.
questions? We're really over time. I'm sorry for that, but I didn't want to cut the BBR questions. Yeah, well,
Can also
let's
do
have
it
one
offline
at
if you
least.
want.
And you can get ready in the meantime.
Mia Kulin, I could also talk to Ronan later, but anyway. So I like the fair queuing approach. That's really nice. Just one comment. So you use the overall minimum round-trip time I've seen. But I think you actually, you try to make really hard sure that you empty the queue from time to time, right? So you could actually try to, when you think the queue is empty, then take a new minimum round-trip time example. That could probably improve your algorithm over time in various scenarios and make it more stable. It's my experience.
I mean, it does actually. So it empties the queues always, and when it crosses the target. So there's this Taylor decrease where you just
no, I mean, just make sure, because you might have route changes or whatever, that you actually not take the overall minimum, but because you know that you empty the queue, just take that minimum at that point of time. Yeah, that's small comment.
Yeah.
All right. Well, thanks.
Good afternoon. I'm David Hayes with Simula, and
Into the pink box, please.
Sorry, I'll be talking about work I've done with a number of other people, and the last two, especially Lars Erik and Hugo, have been implementing this work into Linux. Thanks. What we're looking at is the problem where you have large amounts of data that have to be transferred over the internet. They don't have to be transferred as fast as possible, so perhaps we can send them in a less than best effort way. But they also have a timeliness constraint. Next slide. And because of that, they often have to be completed by some sort of soft deadline. We'd like to have a sort of a deadline-aware less than best effort. Now what that is, next slide, thanks, is it'll have these sort of qualities. It'll be something that keeps disruption of current best effort flows, web things and other types of traffic to a minimum, so do good, and react earlier to congestion than a normal best effort flow. Be pragmatic in that you still want to meet a deadline, and if things are bad, then be more aggressive, but still do no harm and never be more aggressive than a best effort type flow. Next, thanks. Now, our approach was to model this first to get an idea of the dynamics, and then we've developed a framework, a way of doing this that can adapt, in principle anyway, any underlying congestion control algorithm to do this. We have a publication there that you're welcome to look at. Next, thanks. Now, a quick overview, probably the quickest you've ever seen, of network utility maximization. You have senders and receivers through the internet, and one of the ways to model this is, next slide, by saying that the senders try to maximize their utility. They get more utility for particular send rate, but the restriction is that they can't collectively exceed the capacity on any link along their path. Okay, next slide, thanks. Now, it very nicely happens that if you work with a Lagrangian dual to solve this optimization, then it can be solved distributively, and it sort of looks a bit like TCP, where you have a price, but the price is not dollars and cents in this case. It can be loss, ECN, delay, or other congestion type ways, and you do a calculation based on your price to get the rate you send, sort of a bit like what TCP does on average. Okay, next, thanks. Now, if we want to make this less than best effort, there are really two ways you could do this. One way is that you could change the utility function to make it less than best effort. And that's the equivalent of changing the congestion control algorithm. Now, the other way you can do it is you could inflate the price. Okay, so if you inflate the price for one congestion control algorithm, then it will think there's more congestion than there really is and send slower. So that's the other way, and that's the way we're looking at in more detail here. Next, thanks. Okay, congestion price inflation. So you have the sum of the total price that you've got for your whole link, which could be your RTT, or could be your loss, or your ECN signals, and we weight that by a number between not quite 0 and 1 to get an inflated price. If the weight is 1, then it's best effort. If it's not 1 and less than 1, then we have a degree of LBness. Next, thanks. Now, to control that price with respect to the deadlines, then at short time scales, the congestion control will just react as normal, just work as it normally does to the inflated price. But at longer time intervals, we want to keep the idea of the deadline involved, so we will adjust what that weight is relative to the deadline, and we've experimented with a couple of ways of doing that. A PID controller, which is not too bad once you sort of configure it, because you're always controlling something between 0 and 1. And one I'll be showing here is a model-based control, because a lot of TCP algorithms have good models describing their average behavior. So that's one of the ways we've looked at. Next, thanks. Okay, the first thing we did was apply it to Cubic. Why this? Cubic's not the best for this. Yes, that's we know. But if you have a network where most things are behaving like Cubic, then it's like with like. Two ways you could do it: inflate the response or inflate the price. That's the indirect way. We tried this just because just changing the beta seems easy. It turns out that that's more complicated to do in an actual Linux kernel, just for one particular flow. What we did do is look at inflating the price. You could say we drop extra packets, but that's not very nice. It's like shooting yourself in the foot. Instead, we introduce a concept called phantom ECN signals that allow the loss-based protocol to react in an ECN-like way, but without actually losing anything. Next, thanks. Now, as a simple test scenario, we've set up 6 cubic TCP flows starting and stopping. To note, in a short interval between 1,000 and 1,010 seconds, there's nothing except the background traffic, which is 10%. And then the deadline-aware less than best effort flow, if it could send at 10% for the whole time to the deadline, that's all it would need. But of course, we want it to adapt to congestion. Next. So this is what we get when we try to vary beta. And the reason why that doesn't work so well and doesn't give you a good amount of LBness as such is because Cubic's quite aggressive and loss is not a very regular signal. Okay, it's a rarer signal, so Cubic is rapidly ramping up again. Now with Phantom ECN next, we get a better degree of LBness, you could say. However, one problem with this is, how do you know when congestion goes away? Well, you know because there's no loss, but loss is quite rare and it takes you a while to work out that congestion has gone away. So as a result, at the time when nothing else is happening, this sort of thing can't actually take advantage of the spare capacity that's there. Now, if we weren't using loss to detect that congestion was gone away, but something like delay, we could probably do a little bit better. So we chose, next slide, to do this with Vegas eventually, because it's a common delay-based protocol that everybody's quite familiar with. But the problem with having something like Vegas work in a network where all the other flows may be something like cubic is, especially when the deadline's approaching, how does Vegas ramp up enough to compete with cubic? How do you make congestion controls where one's working with loss and another's working with delay actually work together? And Tang and co actually looked at this when they were trying to make it work with fast, but it sort of half worked and they had to put a little fudge factor in, well, quite a big fudge factor to make it work. But we've sort of extended that idea to do it a little bit better. Next, thanks. And what we do is we build a composite congestion sort of parameter based on loss, delay, and ECN, and weight it. And it's a weighted probability we calculate, weighted by the particular congestion control's reaction to congestion. So cubic, it might have a beta of 0.7 or 0.8. Something like Vegas, it's +1, -1, but what's that? Well, if your window size is 2, -1 is 50%, but if your window size is 100, -1 is 1%. So relative to that. But Vegas also reacts to loss, so you've got to handle the both of them as well. Next, thanks. You're getting really good. Okay, sorry, next slide. So what we do is we inflate like we did before, inflate the delay part, but we have this extra parameter phi, which gives us sort of a balance between the aggressiveness of cubic and Vegas at that particular time. So we're measuring the relative reactions to congestion. And we inflate that. Now the loss part, because Vegas is reacting to both of them, when it's really congested and we're getting near our deadline and we want to compete a bit more like cubic, then we probabilistically ignore some losses there. Okay, but we are never, in the end, more aggressive than cubic because we keep track of what a loss-based flow would be reducing relative to what we're doing. Now, this is an example of the Vegas-based one. Now, it's less than best effort. It is reacting on short timescales to the congestion that's happening. When there's nothing at all, it can take all of the capacity, which is what we want to be able to do, take advantage of empty capacity. And, well, in this case, it slightly misses its deadline. Now, we could adjust our control to make sure that didn't happen, but in our case, it's a soft deadline and we'd rather be nicer than more strict to the deadline in this example. Okay, next, thanks. And next again. Now, a little more ambitious experiment. We set up, in this case, trying to look at more realistic traffic. Next, thanks. So we used tmix and based on some real traffic traces, so ended up with hundreds or thousands of concurrent short and long and all mixture type TCP flows starting and coming all of the time, and then had our competing deadline aware less than best effort flow with that. Next, thanks. And we did a bit of work making sure that it was all stationary so we could collect proper statistics from it. Next. Now, this is one of our summary statistics. I'm only going to show one where we just looked at what your completion time is relative to the offered load. That's not the actual load because the actual load will depend on retransmissions and other things because it's TCP happening there. And what you find is that the cubic-based one, because of the phantom ECNs and not being able to take advantage of all the capacity, yes, it always does quite good as far as the deadline goes, but when there's not much happening, it can't actually send our bulk transfer as fast as it should be able to and do it without disturbing the other traffic. The Vegas-based one actually can. And some of our other results, which you'll have to wait to the next publication, actually show that the impact on other types of traffic the other traffic happening at the same time and so on is very minimal with the Vegas and more with that, and much better than if you have, say, a normal best effort flow. And we also look at fairness and some other measures. Okay, next, thanks. Now, where we are at the moment is we have a mostly working standalone version of this in Linux. Part of it involves some kernel modifications, which Lars-Erik has been doing. And then we have what's called a libda LBE module, which the application talks to at the beginning to open a connection to tell it how much data it wants to send and what the deadline is. And then that opens the connection, but the application talks directly to the kernel as it normally would when it sends data. In the background, this meta control is collecting stats from what's happening in the kernel, what the loss, how many packets lost are, what the delays are, and so on, to calculate those parameters so it can adjust through the control the dynamics of whatever underlying congestion control we happen to be using. The examples we had was Vegas and Cubic, but it can be applied to any of them. Thanks, next. Next step is we're in the NEAT project, which you'll find more about in the TAPS working group, but we're going to put this as part of the NEAT framework. So NEAT, sitting over the top, will, when an application opens, wants to open a connection, NEAT will have a look at what congestion control algorithms are available, which one might be the best one for deadline-aware, less than best effort to adapt. If there's a delay-based one, that's usually better. If not, we'll just use Cubic or something. And, well, sorry, back one step. And choose it underneath. You can read more about it there. And in the TAPS group, more about NEAT. Next, thanks. So this is how it works in NEAT. So we have the NEAT library, applications talk to NEAT, but there's all this fancy policy manager stuff, and we keep statistics on what's happened for previous flows so we can choose better and so on. And we still have the same bit in the kernel. Thank you. Next. Okay, this is the last one we'll show. No need to go after that. No need to go to the next slide. So our deadline-aware less than best effort mechanism, it is for bulk type transfers where you want to complete within some sort of loose deadline but be nice to all the other traffic that's flowing. Okay, it's sort of based on the network utility maximization idea. We inflate prices. We tested it with Cubic and Vegas, but in principle, it could be applied to any type of congestion control algorithm working as a meta control. And our ongoing work integrating to NEAT, we have some large-scale tests which we're working with one of our partners, Dell EMC, across the internet with some live tests as well. Okay, thank you.
Just a quick question, anybody? I'm very sorry for this, actually. You know, we should have asked for a longer time slot, but then the presentations that came in were too good. So I sent emails to people asking them to be short, which isn't easy. But all right, it reminds me of the good old days of you know, too many presentations coming in, which is a good thing. So, okay.
Hello, everyone. I'm going to talk about LEDBAT++. It is a low priority TCP congestion control, which we have actually shipped in Windows for several scenarios. Next slide, please. The background, so an anecdote, so basically Windows crash dump upload basically took out in-flight Wi-Fi. So that's how we started looking into this problem. So our goals were that we want to do less than best effort service, but we don't want to interrupt foreground traffic like interactive web pages, Skype calls, and things like that. We basically did some literature survey, and then LEDBAT seemed like the best solution because it ramps up when there is no competing traffic and yields to foreground flows. But we did find problems with LEDBAT, which led us to make some improvements. Can you go to the next slide? Quick recap. So LEDBAT works by measuring the base delay, and then it adds its own target delay on top. And it basically, if the delay is less than target, then there's an additive increase. If the delay is higher than target, then there's an additive decrease. No particular strict requirements on slow start. And it reacts to packet loss just like standard TCP. Next slide, please. So these are the problems that we found. So one-way delay measurements, which was required by the RFC, is hard to do with TCP. So there is no standard clock frequency or synchronization, and there are clock skew problems. There's a latecomer advantage problem because it's a delay-based congestion control. So flow that arrives later measures a higher base delay, and it basically gets a higher share of the network. There is also an inter-LEDBAT fairness problem. So if you have two low priority connections competing, then essentially there's a stable queue, but they don't each get the fair share, even if their base delay is measured as the same. The recommendations around slow start were vague. So that was another thing we thought was a drawback with the RFC. There's also a latency drift problem that we noticed, which is if you let the LEDBAT connection run for a long time, like longer than 10 minutes, we noticed that the base delay would actually keep increasing because of the queue that was built up by the LEDBAT connection itself. So we would notice this latency ratcheting problem, which would keep increasing. And then there's the low latency competition problem, which is if the queue never builds up, if it's a fast enough network connection, then LEDBAT basically behaves like standard TCP and doesn't yield to standard TCP. Can we go to the next slide, please? So basically, we did these essentially 5 changes. Instead of one-way delay measurements, we used round-trip latency measurements. So slower than Reno congestion window increase. So the gain factor, we actually made it adaptive versus using a fixed value. Instead of additive decrease, we do a multiplicative decrease. So and then modified slow start, and then initial and periodic slowdowns so that we can more accurately measure the base delay. This has been shipping since the Windows 10 anniversary update. It is in use by the error reporting service as well as peer-to-peer Windows update. We are working on making this API public and the configuration as well. Next slide, please. So what are the advantage of round latency is that it's already available in TCP. There's no need for clock synchronization. The disadvantage obviously is the receiver delays and the delayed acts. So we did some mitigations here. We enabled the TCP timestamp option implicitly. We filter the RTT samples just as recommended in the RFC to the minimum of the 4 most recent samples. And we use a target delay of 60 milliseconds, which is different than the one recommended in the RFC, which was 100 milliseconds or less. We basically picked a value that was higher than the typical server-side delayed ACK, and we found that 60 milliseconds works much better for Skype versus 100 milliseconds, which covers 2/3 of the budget for a good quality VoIP connection. Next slide, please. Slower than Reno. So essentially, instead of growing the congestion window in the congestion avoidance phase, like standard TCP, we basically introduce a factor which is makes the congestion window growth a fraction of standard TCP. Essentially, F, we experimented with fixed values for F, but it never worked out very well for connections that are a wide range of base delays. We find that picking an adaptive scheme actually works much better. Essentially, we find that 16 is a good trade-off for essentially low latency connections to not eat a large share of the bandwidth when the latency is low. So this essentially solved the low latency competition problem. So I'll be showing a bunch of graphs later which explain this in a little bit more detail. Next slide, please. Multiplicative decrease was proposed in a paper, but we found that just implementing a multiplicative decrease factor was not good enough to solve the fairness problem. Essentially, if 2 LEDBAT flows don't have the same base delay, then just introducing multiplicative decrease was not good enough. Essentially, we had to cap the multiplicative decrease coefficient to be at least 0.5 for it to be effective. We also had to ensure that the congestion window never drops below 2 packets. Next slide, please. So slow start, this is interesting. So we did not want to skip slow start because skipping it, we found that it when there was no competing traffic, leadback would ramp up. Leadback plus plus would ramp up very slowly. So we still do a slow start, but we essentially also apply the adaptive reduction factor to the congestion window increase, so that the slow start for a leadback plus plus flow is actually slower. The ramp is slower than a standard TCP. We also limit the initial congestion window to 2 packets. We also exit the initial slow start if the queuing delay becomes 3/4 of the.
Clarification question. You say you add the reduction factor to the increase.
Yeah.
So what's the increase at that point? What's the increase that you do?
So essentially, it would be similar to the multiplicative decrease slide that I showed before. So it will be a fraction of.
So 1 over F.
Actually, 1 over F.
Thank
you. And then, we exit slow start early if we find that the queuing delay becomes 3/4 of the target, which is 60 millisecond value that I described earlier. But we only apply this exit for the initial slow start, because for subsequent slow starts, we do have an SS thresh value. Next slide, please. So we had this latency drift problem, and the way we solved that was by introducing initial and periodic slowdowns. So what we want to do is we want to actually yield to the network to figure out what the accurate base delay is. This is especially important when your leadback plus plus connection is going on for a long time. So to force these gaps, essentially the RFC said that there would be automatically, because of the burstiness, there would be periods in the network where it would be measured, but practically when we did these experiments, we found that that didn't work very effectively. So we introduced this notion of a slowdown. So it's basically an interval where the leadback plus plus connection voluntarily reduces its congestion window down to 2 packets for 2 RTTs. And then after 2 RTTs, we again do slow start until we reach the previous SS thresh value. The initial slowdown starts twice the RTT after the first slow start ends. And then for periodic slowdown, what we do is we measure the duration for the connection to have ramped up from the after the 2 RTT slowdown phase back to the original SS thresh value. So we measure that duration, and then we multiply that value by 9, so that effectively it becomes only a 10% drop in throughput. For let's say there was no competing connections, then we would essentially see only a 10% drop in throughput. This is actually a configurable value, but we found that 10% to be an acceptable drop. We found that this solved the latency drift problem. Next slide, please. I'm going to go over a bunch of measurements. This is basically just showing that standard TCP, when there are other short flows, it basically doesn't yield. And this, the graph below shows that. So the purple graph is basically your short flows, and then the red is leadback plus plus. So as soon as short flows ramp up, leadback plus plus very quickly yields, and it's able to ramp back up when there are no competing flows. Next slide, please. So standard TCP, again, this is the problem. So slow start binds up a bunch of queue, sometimes up to 1 to 2 seconds. These graphs are not in the same time scale. So for leadback plus plus, we see that it achieves its essentially stabilizes around 120 milliseconds of latency. Next slide, please. So this is the ratcheting effect that I was talking about. Standard leadback over time, essentially the period of 10 minutes would keep increasing the base delay. So essentially the ACK delay would keep on increasing. So over time, we find that it goes from about 120 to like 180 and then over 200 milliseconds. Just applying the multiplicative decrease as I described below didn't solve this problem. We had to actually also cap the coefficient as well as introduce the periodic slowdowns. And then we see that we're able to keep the, we don't see this problem of base delay continuously increasing for long running connections. Next slide, please. Standard leadback, yes, there is a latecomer advantage problem. So the yellow flow essentially came in later, and it basically took over pretty much all of the bottleneck bandwidth because of its higher base delay measurement. Leadback plus plus, as you can see, the green flow essentially starts later after the purple flow, and they both essentially end up fair sharing. And the last graph here is both of them essentially accurately measure their base delay, and it's the same value. Next slide, please. This is the low latency competition problem. So when we run standard TCP with leadbat++, but we keep a fixed reduction factor, we see that standard TCP basically only gets 2/3 of the bandwidth. This is the case where, for example, the latency is like 1 millisecond or 10 milliseconds, very low value on the base delay. But once we introduce the adaptive value, in this case, because let's assume the latency is less than 10 milliseconds, we would end up with F as 16, and then we find that leadbat++ yields and majority of the bottleneck bandwidth goes to standard TCP. Next slide, please. So yeah, in summary, we found a bunch of problems with leadbat as described in the RFC. So leadbat++ is an attempt to solve those problems. And our experiments show that it achieves what we set out to do. It's already deployed on millions of systems for the scenarios that I pointed out earlier. We're working on making the API and the NOP public. We are working on a draft submission. I had a question here to the room, whether it should be to ICCRG or TCPM.
As chairs, our agreement, our view on it is that this should be ICCRG, because I mean, well, several reasons I think. But...
And we'll fight for it.
Okay. Questions?
So this is Michael speaking as one of the other chairs fighting for it. I mean, it's a fair question to ask, but in this specific case, I believe the submission could also be TCPM. What would happen in that case is that we would forward it to ICCRG to discuss. So at the end of the day, it would probably be discussed here again. But conceptually, for that specific document, the submission could target TCPM at the end of the day, in my opinion.
I'm Gori Fairhurst as TSVWG chair, which is, I guess, the other possibility. Again, if you sent it there first, we would send it back here. Same answer. So I don't think it matters where you do the adoption. If it's useful to discuss it, write an internet draft would be my encouragement, and then talk about details later.
I don't know how many of you remember my TSV area presentation explaining with the happy trash can of the IETF, but it's our role. It's always been our role. So, bring us the stuff first and we'll deal with it until it's ready for you guys.
Jana, I'll say that, yes, I will actually fight for this. And I specifically, I say that because it's a condition control. It's a condition controller, and ICCRG has condition control in its darn name. But let's not litigate that here. I do have one particular bit of feedback. It seems like there are two separable pieces in the work that you've done, and this is excellent, by the way. Thank you so much for doing the work and for bringing it here. This is very, very valuable and useful. Some of the points you mentioned, we knew early on when we were doing that, and it was like the stuff about we were expecting there to be empty or quiet periods in the network. We didn't know, but it's definitely good to know that drift is a real thing. And with BBR also, it's similar. There is definitely drift that happens, and so you want to do that.
Yeah, we did notice that the RFC actually talks about these problems, even entered leadbat fairness and latecomer. All of those things are talked about, but we didn't find a good solution, so we had to go build one.
So I think the separable pieces are, one of them is actually a direct update to the leadbat algorithm itself, and the second one is making leadbat useful with TCP. And I know that folks at Apple have implemented leadbat with TCP as well. So I think there may be value in separating this into the algorithmic part and how do you make it work with TCP. And those two pieces could belong in different places. That's just a bit of input, but I would like to discuss the question of where it belongs, maybe not right here.
Thank you.
Just for the record, I'm cutting the line after Michael Scharf, just to be sure.
Lars Eckert, so the original leadbat was experimental, but done through the IETF track. And since it's been seeing quite a bit of deployment, right, and there are fixes that are looking very interesting, and they're made based on actual running this thing, I would hope that we could make the follow-on standards track, right? The original, it seems to have problems that maybe we don't want to do it with that, but this one might be, right? And if we're doing a standards track, it means means it needs to be done to the IETF. Remind me to not have beer at lunch again on Monday. So that still means that so I like the split that Jana proposed as a possibility, right? That means that the algorithmic part doesn't necessarily need to be standards track, but it might also be. I mean, going on a little bit of a rant here, right? We have done data center TCP as informational. We've done Cubic as, I think, informational experimental. We're now talking, so Cubic isn't even published, and we're already talking about adding it to the downref registry so that RFC, standard track RFCs can point to it. So I think we are too cautious with doing stuff on standards track.
So I'll quickly respond to that with the chair hat on. I don't think that condition controllers need to be standardized. I said this in the past, but that's my short response.
Your co-chair disagrees. I don't know. Okay.
Yeah, Spencer Dawkins, Transport Area Director. I'm happy to watch you all work this out and try to be as helpful as I can. The thing that's probably worth me saying here is for asking you all to think about who else would see the work in the IETF. And I'm talking people in other areas. If that's a if that's a consideration, it's worth considering. If it's not a consideration, forget I said it. I am curious how much more work you think needs to be done here. I mean, like, do you feel like you're through, or?
So one of the problems that we haven't solved yet is working well with AQM. Now we do have some solutions here, which I have not talked about in the slides, but that's a work in progress. So that's the only part that remains to be figured out as far from our side. But of course, there could be other feedback from the community, and we'd be happy to address any kind of gaps here.
Yeah. Cool. If you're thinking that there is still research to be done, and I'm actually also on the IRSG, so I get to have that conversation. If you think that there's still research to be done, I think that doing it in a researchy kind of place could make a lot of sense. But like I said, I think I don't have opinions about where it should end up because I don't understand all the things that need to be balanced. But those are the things that I was thinking.
Thank you.
Okay, thank you. We have one more person, but I'll ask for an elevator pitch, just overview of one slide, just to give an idea of what it is, and then we have to cut this. I'm really sorry for that, but just come on out and tell me which slide to show. Pick one or two slides.
How many times after?
You have 0. We're 1 minute above the end, so there is no more time really. That's why I sent you an email saying it has to be an elevator pitch. You just have to tell what it is. You can just say one thing about the what?
Or quickly go through.
Not go through. No. You talk about one slide about what it is.
Okay, so go to
Is it this maybe? Okay, then we just go there.
Actually, this is the draft of our work in the research to provide the transport service for the ultra high bandwidth and ultra low latency application. And basically, the motivation is to try to do something which the current transport cannot support, such as AR, VR, and tactile internet. And based on the analysis of all historic solutions.
You need to talk into the microphone. We can't hear you.
Based on the analysis of the current solution, we take the approach that the network device will be involved more in this regard. And so we also want a simpler solution, protocol to support this. We try to get rid of the same fate of the ISVP. So our design target is that the end user or application can directly use the new service, and also the new service can coexist with the traditional TCP, and both can share the resource of network. Also, the quality of service can be adaptive to the application requirement, which means the application can directly change it. So the service provider can also manage the service. And the performance and the scalability, this is the most concerned part, which we think the target should be achievable by the vendor and the hardware. Also, last one is that new service is transport agnostic, means that both TCP and UDP can use it. So I only have time to go through this slide, but if you are interested, please read the draft, which was submitted to the 6 man first. But because we have a lot of other areas to do, like congestion control and security and the UDP, so this draft is the first introduction of the ideas, and we may have other work to do. So if you're interested, give us feedback. Thank you.
David Black is TSVWG Chair. Public service announcement. This draft is on the TSVWG agenda for Friday, where Lynn will have a lot more time to present it and talk about it. Great. Please show up for that.
Yes.
Great.
Yes.
Thank you very much for putting it on the agenda. Yeah. All right. Thank you. Apologies for this, and thanks all for coming. If blue sheets are here, if you didn't get to sign the blue sheets, then come out here and do it. And thank you. This ends ICCRG for today.